time to relax and de-stress for a minute. But other than that, I'm going to go through a couple of announcements. Know that I know that you're all busy and I know you're all stressed out. And so I'm here if you need me. And that's why I'm also going to offer some review sessions that I'm going to record and post for exam 4. Okay. So announcements for this week. You're going to have your final quiz, your last quiz on Thursday. All right. What else? The lab that we're doing this week is in person. So that's exciting. I get to see you all one more time. So we get to hang out and do the vinegar titration. And that assignment is due Sunday. And that's your last lab. So ends of quiz, no more quizzes and no more labs after this weekend. The chapter 10 homework is up and it is running. It is available. Here's a bonus. I'm going to work a homework problem in today's lecture just for you all. Merry Christmas. Okay. So that's part of today's lecture. And that is due, the homework assignment is due next week. And then what else? The exam is a week from today. Sorry, I had to throw that one in. All right. I think that's all the announcements. A couple of reminders. You can get some bonus points and they're total participation points. So if you do the eval, you get 5 bonus points automatically on exam 4. Just send me a screenshot of some kind of confirmation that you did it. When is the homework due again? Monday evening of next week. Yep. Thank you, Adam. The 26th. I think that's it. Do the eval. Oh, another announcement. I just sent an email. I would love actually for somebody to just click on the link and make sure it works for me. I sent an email that is eliciting your feedback on mastering chemistry. So most of these questions are multiple choice, and then there's like 2 on there that are optional if you have any other feedback, good or bad. The link does work, and I just did it. Okay, thank you. Thank you, Glenna and Mackenzie. Good. Mackenzie said, how do we submit the eval? So you should have some place on MyUCA that you can go to do evals. And I think people should be, some sort of administrator regularly sends emails that says, hey, do your evals. Do you access it through MyUCA? I know a lot of you have already done it. And you should just email the picture that you completed it. It should be on your Blackboard dashboard. There we go. Thank you, Erin. Blackboard, not MyUCA. Well, Blackboard is through MyUCA. But so if you do that, 5 bonus points on exam 4. The final is comprehensive. I'm going to have lots of review for the final. So we're going to do chapter 10 today and Thursday. And that's it. We're done with all the content in this course. And unless I do a short video on functional groups, but I don't know if I'm going to have time for that. So then next week you do the exam, and the next Thursday, which is the very, very last day, we're going to review. We're going to start with chapter 1, and we're going to review. I think I'll get through chapter 4 is usually how it works that Thursday. And then I'll continue the review the very next day. So on the study day, Friday, stop it, guys. Listen, functional groups are very, very important for people taking Chem 2450. So I'm trying to think of those people. And I know that's not everyone, but some of you need it. So we'll see. Then we're going to finish the review on the study day, okay, for the final. And then your final is May 6th. I don't know what day that is. Is it a Thursday, maybe? May 6th. The time is listed on the syllabus schedule, okay, on our lecture schedule. If you have any questions about it, it's not optional. You have to take the final. If you don't take, one time I had a student who thought the final was optional. That was very bad. I felt so bad. I mean, I didn't feel bad, but I kind of felt bad. So just don't think it's optional. That's it. Okay. Any questions from you guys? You guys are chatty this morning. I like it. All right. I'm going to give you a little preface. What we're covering today is kind of like just setting us up for Thursday. All right. So it's kind of a downer in that, but it's still important. And it's going to be fun. And so let's get into chapter 10. I'm going to remind us of a few things that we are or already have gone over. All right. But don't think today is purposeless. Today is going to be setting us up for pH, which we're really getting into pH and buffers on Thursday. And those have huge, huge, huge biological significance and implications, okay? So we have gone over how to define what an acid and a base are, okay? How do you identify? We did this practice problem right here, where I had you go through and identify which one's the acid, which one's the base. You guys remember that? Then we looked at conjugates. Okay, we said every single acid and base, when they react, they produce on the product side a conjugate acid and base, and we identified conjugate acid base pairs. All right. And then we practiced writing those out. And then we ended with this problem where we talked about this molecule that is amphiprotic, meaning it could act like an acid or a base. It could do both. And we wrote things out there. So hopefully you have assessed a few of the homework problems, because you do have some skills and some tools to answer, a portion of the homework problems. Please do it a portion at a time. Like, do 5 or 6 problems today. Click through. You don't have to answer all of them. Just click through and do the ones you know how to do. And then as we finish up Thursday with pH and buffers, then go back and answer the questions on pH and buffers, okay? That's my suggestion on how to do the homework assignment, so that you don't save all 30 questions or however many there are for Monday, the day before the exam, and you're stressed out. Okay, don't do that to yourself. That's one way to cope with stress, is proper managing, right? Okay, so we're going to talk about acid-base strength. And we need to understand this idea that not do we just have acids and bases, we have varying strengths of acids and bases. So I'm going to ask you a question. If I gave you a beaker and it either had acid or vinegar in it, well, I gave you 2, one of each. Which one would you be willing to take a drink of? That's a dumb question, right? We all know which one we should and should not take a drink of. So obviously you would be willing to ingest which one? Which one would you drink? Which one could you drink? Probably still wouldn't taste good. Thank you. Vinegar. Does anybody do like the drink of apple cider vinegar every day? Isn't that supposed to be like Hunter, you do it? What are like the health benefits? We need to know. Anybody else do this? I've heard it's good for you.
It's supposed to be good for your gut, but the first time I did it, you're supposed to like mix it with water and honey, and when
And
you
you
first do it,
didn't?
because it's really bad. And I put it in like a shot glass and tried to just take it, and I wanted to cry for like 10 minutes straight.
Oh man. Keegan said, what a man. Okay, well that's good to know. So you can ingest vinegar if you so choose. I have not. My sister is a dietitian. She said that it does nothing and it's all of it. So okay, wow. Dang. Pineapple juice. Okay, well, I have a friend, she drinks straight celery juice. So anyways, back to acids and bases. HCl, we know, obviously is highly corrosive. Okay, so anything that's highly corrosive is going to eat away at things that it's in contact with. While vinegar, or I should say acetic acid, V-I-N-E, I'm not spelling this right at all. There we go. Is edible. We can use it in cooking. I used to make poached eggs. Anybody love like eggs Benedict, and you put vinegar in the water to cook your eggs? It's really good. But what this depends on, how we get different strengths, is it depends on how easily the acid disassociates. And what do I mean when I say that word disassociates? What did we say that indicates? What's happening? Thank you, Grayson. Apple cider vinegar will rot your teeth out. Sounds like candy. That's what my mom used to tell me about candy. Yes, disassociates is when it gives up a hydrogen. Okay, so we're going to literally draw the disassociation reaction, or between a strong acid and a weak acid reacting with water. Okay, so obviously HCl here is the acid, and down below the acetic acid here is our acid. And both of these have acidic hydrogens right here and right here. They're going to give that up. Water is going to be the base. So it's going to accept the hydrogen. What on water accepts it? The lone pairs. And when that happens, we have Cl minus left over. And we're going to get what? What's our other product? H3O plus. Hydronium, or, that's interchangeable with just H plus. What I want to make a big deal out of is my arrow. Okay, I'm drawing a single directional arrow, not a reversible arrow. What this means is that this is going to completely disassociate. Okay, completely. So let's do a little thought experiment here. I'm going to zoom in. If I have 1,000 molecules of HCl in my beaker with some water, by the time it's done initially as well, so if this is initial concentration, which it's not technically a unit of concentration, but if this is my initial amount, then I initially also have 0 products, right? Initially. Okay, when I'm done, finally, what will I have? If this is a complete acid and it will 100% disassociate, how much HCl, how many molecules of HCl will I have left in my beaker? Mm-hmm. 0. I will have 1,000 of these and 1,000 of these, okay? Keep that in mind. We're going to come back to this idea later. But it's not the same thing with weak acids, okay? Weak acids partially disassociate. All right? So maybe 40%, maybe 50%. It's different for every weak acid. So I'm not going to write the 1,000 and 0 thing here because we don't really know until we have more information. But what we do know is we're going to have a double arrow. Okay? You're going to make products. What products will we get? CH3COO minus and H3O plus. But we don't, it's going to be a partial disassociation. You'll have a forward and a reverse reaction. Okay? So keep that in mind, how you differentiate between strong and weak acids. Strong acids completely disassociate, weak acids partially disassociate, okay? Single arrow and reversible arrow. Bases do the same thing, all right? In case anybody's still writing, I'll leave right there. Strong bases have a very high affinity for H+, so they bind the hydrogen ion tightly. They almost like rip it off of the acid, okay? They go get it. And then weak bases have a low affinity. If they're around a really strong acid, sure, they'll take the hydrogen. But if they're not around a really strong acid, they may not want to accept the hydrogen very much, okay? So they bind hydrogens weakly. So we could draw the same kinds of reactions with strong base and weak base. NaOH is a really strong base. So I'm going to draw a single directional arrow. A weak base, ammonia is an example, NH3. I'm going to draw a double arrow. What products are we going to get? When you do the reaction for the strong base, it's going to feel very redundant. You're going to almost get the same products on both sides. Think about it. Why is that? Here's our base, OH minus. It's going to grab a hydrogen off of water. What do we make when we get OH plus a hydrogen? One of our products will be water. All right. And then the other thing we're going to get, what we have left over, we still have our sodium cation. And now what's left over from water is OH minus. So we get Na plus and OH minus. It'll be aqueous, so I'm going to draw it as they're separated ions. You could write NaOH if you want. So look how redundant that is. But strong bases, it'll go to complete, it'll completely grab all the hydrogens. Every single molecule of OH minus will grab all possible hydrogens from water, okay? And I don't mean it will take both hydrogens from water. I just mean that reaction of transferring the hydrogen will happen until there's no OH molecules left. All right, a weak base. So ammonia here is our base. OH minus up here was the base. And we know the lone pair as well. I'm going to grab a hydrogen from water. It's just not going to do it as ferociously as OH minus. So we'll get NH4 plus. Don't forget how charges change. Remember, we said acids give away a hydrogen, so they decrease in charge when the conjugate, we write the conjugate base. Bases are gaining hydrogen, so they increase in charge. That was all part of last week. And then left over from water is OH minus, okay? All right, so again, this is going to be complete. This is going to be partial. Single arrow and double arrow, okay? Just as we wrote with the, okay, Keegan, what are you confused on? Okay, well, let me simplify. All I want you to think about right now is the arrows. Okay. I just want you to think for a strong acid or a strong base, this reaction is going to go to completion. All right. But for a weak acid or for a weak base, you're going to have a reversible reaction. Bradley says, could you explain why the strong base does what it does? Are there some steps to ask yourself to determine this stuff? Okay. Let me answer one at a time. Keegan, did that help? I just want you to focus on that right now. Don't worry about anything else. Single arrow and double arrow, partial and complete. Bradley says, can you explain why the strong base does what it does? Like, why does H2O not change? Bradley, what do you mean? Why does H2O not change? By the way, I'm about to get to a table of acid-base strength, in case y'all are wondering. Like the product was still H2O. Oh, Bradley, this one just here is because, so water is our acid in this case. What did we say acids do? Acids are proton donors. That's what we nickname them. So it's going to give up a hydrogen. So think about it. One of these hydrogens, just one. Right now for water, water looks like this, H2O. Okay, so if it's just going to grab one hydrogen, I'm just going to say OH minus and H right here. This hydrogen is going to get, this water molecule is going to give up that hydrogen and it's going to combine with that OH because that's the base. The base is going to accept the hydrogen, water is giving it up. So we're going to make water again. It's not that we still have the same exact molecule. The molecules are changed. It's just that redundantly we make water in this equation. Okay? That's why we still have water on the product side. But an acid-base reaction did occur. Okay? Does that help, Bradley? Maybe. Okay. Danielle, we're not actually working particularly a problem right now. I'm just laying out some concept stuff for you to be able to work problems. So I'll give you some steps when we actually go to work a problem. But the main point here is I want you to understand there's strong and there's weak. Okay. And I'm not going to ask you to memorize a whole table of strong and weak acids or bases, but I do want you to be familiar with this concept. And what that concept means is that you get complete dissociation or you get partial dissociation. Okay, so let me move on just a little bit. I don't want to ignore questions, but I think if I keep going, I think completing the topic will maybe help. But I'm going to pause after I do another slide or two, and then I'm going to ask, are there any questions from people who are still asking stuff? So like right here, this is a table out of your textbook, okay? And again, I'm not asking you to memorize any of this. I'm going to give you this table on the resources page, but I do want you to know how to look at it and then determine if something is a strong or a weak acid or a strong or a weak base. Okay, so on the left side, we have the acids. So everything on the left side of the table are acids. And what this arrow shows right here, I'm going to put a star by it. As you start from the bottom and work your way towards the top, at the bottom is the weak acids, and then it's climbing in strength. Okay, the top up here we have the very, very strong acids, so they will 100% disassociate in any solution. At the bottom we have very weak acids. They will only partially disassociate in solution. And then look, water is even beneath that because we really don't consider water to be an acid unless it's in the presence of a strong base. Okay, so if I were to give you a problem, say, is this a strong acid or a weak acid, you could come look at this table and identify, or if I said put them in order of increasing strength or decreasing strength, you could come look at this table and identify that. Conveniently, on the right side of the table, it shows the conjugate base. And we know what conjugates are. If you're confused on conjugates, I'm not going to take time to re-explain all of that. You can recheck the lecture video from last Thursday or recheck your notes and slides. But it shows the conjugate base. So these are a bunch of different bases, and we increase in strength as we go down. So here's what this means. If you're a really strong acid, so look at the top left corner, what do we see? HCl is one, HNO3, these are strong acids. Their conjugate bases are the weakest bases, all right? So NO3 minus really doesn't want to accept a hydrogen very strongly or tightly, all right? But HNO3 is a really strong acid. It will completely give away, whoop, I just hit my cup, all the hydrogens, right? So again, little or no reaction as bases for the conjugate bases of a very strong acid. But as you go down and you get weaker and weaker acids, these make, it says weak bases, but they're stronger than the ones above them, stronger and stronger bases, okay? All right. So if I gave you a list of a few acids and I said, write their conjugate bases and order the conjugate bases from weak to strong, you should be able to do that from looking at this table. You could write the conjugate bases and then looking at the arrow, you could order them from weak to strong or strong to weak or whatever, okay? All right, are there still questions? Does this help at all a little bit? It's a dangerous question to ask right now. Okay, I'm gonna go to one more topic though. Now, here's why I was making a big deal about the arrows, because there's something we can do with weak acids, all right? Because the dissociation of a weak acid is an equilibrium. Why is it an equilibrium? What's an equilibrium? An equilibrium is when you have a double arrow. You have a reversible reaction. So you have the forward reaction and the reverse reaction. We said equilibrium is when those are happening at the same rate. All right, you're making your initial product, or you're making your products the same rate you're remaking your reactants. That's equilibrium. That was all chapter 7, remember? So when we have an equilibrium, we can write an equilibrium equation for that dissociation. And I'll let you tell me how you feel about that. All right? None of your smile. That's how I feel about it. Okay. So let's look at an example of just a very general equation for a weak acid. All right, we have HA. Remember, that's how we abbreviate acids. There's the acidic hydrogen, and A stands for acid. And if it's with water, we're just, again, this is a very generalized example if it's with water, because all acid-base reactions happen in an aqueous solution. We're going to get a double arrow, and our products are going to be this, H3O plus and A minus. So this is the conjugate acid. This is the conjugate base, right? Now remember, we can, H3O plus is interchangeable with H plus, right? Those are interchangeable. So if I said we made H plus and A minus, or we made H3O plus and A minus, same thing. Now remember that K is our equilibrium constant. So we can write an expression for K, that's what we're about to do, which equals the concentration of products over the concentration of reactants. That's what K is for any chemical reaction. So let's write that out. What are our products? K for this one is going to be concentration of H3O plus over the concentration of A minus divided by concentration of HA and concentration of H2O. These are multiplied. So H3O times A minus, HA times H2O. I'm just plugging in my reactants and products. Products on top, reactants on bottom. Remember, if we had coefficients, they would be raised to the power of their coefficients, but all of our coefficients here are just 1. So I don't have to write those in. All right. So this is like a regular K. The only thing is, for a weak acid, we make one modification, and it's a very valid one. So let me explain. We're going to do one modification from regular K because we're dealing specifically with an acid. Even though, let me read this. Zoom in just a little bit. Even though water is a reactant, it is also the solvent. Remember, solutions have solute and solvent. Solvent is like what the solute is dissolved in. Okay, so water is a solvent here, which means the concentration of water is huge. It's so much bigger than any other reactants or products. So we would have billions of water molecules and maybe only, like a couple thousand of our acid molecules. All right. So if we're factoring that into our equation, the concentration of water is going to totally dominate. All right. The H2O concentration is not significantly changing or affected when the acid dissociates. It'll still be really, really, really huge. And we would always drive K to like a very, very small, infinitesimally small number. And we just wouldn't know anything about K. So because K could be valuable for telling us about the strength of the acid, we need to take water out of the equation. So that's what we do. We group water, we just pull it out of the equation. So just take it out. And essentially we group it with K and we write it as now Ka. So instead of just calling this K a random K for any equilibrium expression, we have a specific K for weak acids. All right, so here's what that means. We just call it K of water, we call it KH2, or sorry, Ka. And Ka is equal to the same things as above, we just took water out. The same thing we wrote up here, we just took water out. That's what Ka is equal to. So this is K for Ka is an equilibrium expression for weak acids. And this is still just as usual, our products over reactants. It'll just be reactant because we took water out. All right. So we're going to use K. I'm going to tell you a little bit more about K in a second, but why do we only do this for weak acids? Why do we not write Ka for strong acids? Thank you, Hunter. Strong acids completely dissociate. Okay, we get a single arrow. Okay. So it's not reversible. No reversible reaction. Yes. Kayla says, can I go back up a bit? Do you want me to go up farther than this? Okay. All right, so far we've entered into this idea that there's strong and weak acids. And we're trying to get some useful information out of that. So we know weak acids, we can write an equilibrium expression. And now we're going to see how is Ka useful. All right. So here's how Ka is useful. So here again is just a general equation. Ha stands for the acid. Water is the solvent, so water is present. And we get the products H3O plus and A minus, and we can write this corresponding equilibrium expression for that generalized acid dissociation reaction. Okay. So Ka directly tells us about the strength of the acid. This is why this is important. Earlier I said we know, so like if we had 5 molar HCl, we would know what the concentration of the products are because it completely dissociates. But for a weak acid, maybe it only 50% disassociates. Maybe it only 20% disassociates. So we have to have some additional information to tell us about the strength of weak acids because we have a whole gamut of weak acids. All right. So Ka is going to help do that. It directly tells us about the strength of the acid. How? Well, the larger Ka is, the more that the products are favored. Remember equilibrium? You could always tell me at equilibrium, are the products favored or the reactants favored based on the size of K? Remember, little review here, if K is much, much bigger than 1, products are favored. Whoop, whoop, whoop. If K is smaller than 1, reactants are favored, okay? All right, the more the product is favored. The only thing with K for weak acids is pretty much all of them are going to be smaller than 1, all right? Now you are still going to have a range of Ka values, but they're all going to be small. So we're going to have to work within a framework of small Kas and then compare them relative to each other, okay? But let's keep going. The product is the dissociation. Remember, dissociation is when the acid gives up its H+. So when it does, that's when we go make our products. the more dissociation we have, the larger Ka, the more dissociation that happened. And the more an acid dissociates, the stronger it is. So what we're trying to say is that if you have a larger Ka value, you have a stronger, still a weak acid. It's just a strong, maybe it would dissociate 60 or 70% versus an acid that would only dissociate 10 or 20%. Now, again, I want to zoom out for a second. Why is this important? I'm setting us up for pH, okay? We have to understand acids and how they behave before we can understand pH and why pH is important, okay? So I know this is kind of down in the weeds, but hang with me. I promise it's gonna be important. All right, everybody good with this slide? Okay. So I think this table will give us some numbers and give us a little bit of just a more concrete example to look at, because so far it's very abstract what we've been talking about. So this is a table right out of chapter 10. I will also give you this table on your resources page. It just shows a bunch of different, these are all weak acids, except for that guy. He's a strong acid. Can I scroll up some? Yes. So what we're about to do is look at this table of Ka values and analyze it just a little bit. And so look at the Ka values. I told you all of them are smaller than 1. Look at what we have. We have exponents, negative exponents, okay? So for example, ammonium ion, this is a weak acid, but look at the Ka value, 5.6 times 10 to the minus 10. You know what that is? That's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 5, 6. That's how small that number is, okay? So we're dealing with really small numbers way smaller than 1, but we can still compare them relative one to another. So on this table, could anybody identify the acid with the largest Ka value? Keegan said HF, 3.5 times to the minus 4. Haley said HSO4, and she's correct right here. Okay. So this one, 1.2 times 10 to the minus 2, that's the largest value here. It's still small because it's less than 1, but of the values on this table, it's the largest. So you know what that means? Of the weak acids here, this one is the strongest. All right. So in solution, if you had a solution of HSO4 versus another acid here, the HSO4 solution, that would be the most acidic. The stronger the acid is, if it's in solution, the more acidic that solution is. Does that make sense, what I just said? Okay, on the contrary, which one is the smallest? Which one is the weakest of the weak acids? Tyler says HPO4. Right here. That's the only one with 10 to the minus 13. Now, don't be confused. The larger the exponent, the smaller the number. That doesn't make sense. I thought a larger exponent was larger, but it's a negative, right? So on the negative scale, the larger the exponent, the smaller the number. So this one is the weakest weak acid, right? Okay. So I'm going to actually launch a poll question. If you had a 0.5 molar solution of each of the following weak acids, what solution, which one would be the most acidic? So you need to look at these 4 acids, HF, HCN, H3PO4. H2CO3, carbonic acid, phosphoric acid. And look at their Ka values, and you need to order them. The larger the Ka value, the more acidic that solution of that acid would be. The smaller the Ka value, the weaker the acid, and the less acidic a solution of that acid would be. All right, I'm going to give about 15 more seconds. All right, I'm calling the poll. Share results. Okay, so every answer was selected. The most commonly picked answer was H3PO4. So I'm glad we're talking about this. I think we need to re-examine for a second. Let's look at our Ka values. I'm going to order them. So I'm going to start with the one that's the smallest. Okay, so let me highlight the acids we have here. We have HF, we have HCN, H3PO4, and H2CO3 right here. So now let's order these. The one that's the smallest is HCN. Its Ka value is 4.9 times 10 to the minus 10. That is the smallest, okay? The next smallest is H2CO3. Its Ka value is 4.3 times 10 to the minus 7. Now, I'm not even really looking at the base numbers. You know what I'm looking at? The exponents. A negative 10 versus a negative 7. That's really all I'm looking at. Next, we have HF, which is the 3.5 times 10 to the minus 4. And then we're looking at H3PO4, which is 7.5 times 10 to the minus 3. Okay, so I'm going to make a note. Just look at the exponent. So if we look at the exponent, we've got negative 10, negative 7, negative 4, negative 3. So because this one is the largest, that means it is the most acidic. It will dissociate the most. And because we have 0.5 molar of each of these, we don't have to compare concentrations. We can just look at Ka values and order them this way. Most acidic, so this one would be least acidic. Okay, does that clarify for anybody who was unsure on that one? All right. So that's a little bit on Ka values. And now look what I'm going to do. Okay, if you weren't taking notes before, you better take notes now because I'm about to work a homework problem for you. Problem 10.66. Enhanced with the solution from your instructor. All right, 20% of an acid, it doesn't tell us which acid, but in a 0.1 molar solution, and it says it's a weak acid, disassociates to form ions. All right, so here's what we have. Weak acid, HA. Disassociates to form, I'm catching up in the chat, sorry. Yes, we're just talking about weak acids right now. Yeah, Ka did not have, strong acids do not have K. All right, so this is going to disassociate to H plus and A minus. All right, you could write water in there if you wanted, either way. And starting out, initially, we are going to have 0.1 molar of this before any of it disassociates. And if none of it has disassociated, then initially we have 0 molar of these things. All right, so this is just intro information that I'm writing. Now, it says, what is the H3O plus concentration? You're like, well, I don't see H3O plus in my reaction. Remember, H plus and H3O plus are interchangeable. If I had written the weak acid plus water, then my product would have been H3O plus. But it honestly, either way, If you solve for H plus, it's the same thing as H3O plus. Okay, so we want to know what is our final concentration after it disassociates. Well, it's going to disassociate 20%, right? Anybody have an idea for how we could solve for the final concentrations? So 20% of this is going to be disassociated. So we need to take our percentage and just turn it into decimal form. How do we do that? There we go. So 20% divided by 100 is equal to 0.2. So 0.2 is 20%. And now we're just going to multiply that by 0.1, our initial concentration. Okay, so what we'll have left is, so real quick, I want to do the products first, because if we have 0 of that starting out, what we're going to end with, the concentration of our products will be 0.1 times 0.2, right? That will be our final concentration of that. 0.1 times 0.2. It'll be the same. For every one molecule of acid that dissociates, we'll get one H plus and one A minus. It's not asking what the leftover concentration of the weak acid would be, but we could easily, so let's actually calculate this. What is 0.1 times 0.2? 0.02. So 0.02, 0.02, whoops, 0.2. So then we would know that we could solve for this by doing 0.1 minus 0.02, right? So what would that be? 0.98 molar. Okay, does that make sense what we just did? So that's just an example of a weak acid problem. Now, it says express your answer to 2 sig figs. This is all your favorite part of mastering chemistry, right? So we would just type in 0.02, probably have to put a 0 there. Why do we subtract on the reactant side? We actually didn't even have to calculate the concentration of the weak acid left over, but if you wanted to know what that would be, this is our initial, and we subtracted off the change to get the final. The initial minus how much it's going to disassociate by, which is it's going to disassociate by 20%. 20% of 0.1 is 0.02. So we subtract that off of the initial concentration of the weak acid, and what the amount you're going to have left would be the 0.098 molar. Did that help, Tyler? You always have to figure out by how much is it changing, and a disassociation is a change, and subtract that off. Okay. These next parts, B and C, we could probably come back and calculate part B later. So will somebody please remind me, because I totally forgot with the 8 a.m. group, to come back and answer part B. Part C, we aren't going to cover pH until Thursday. So, but we can come back and do part B, just don't let me forget. But we need to explain a few other things before we do that. So I'm going to put a pin in weak acids. That's it for weak acids right now, okay? If you just feel totally lost still, please reach out to me. I'm going to have a study session 9:30 on Thursday. All right, so now we're going to talk about water. I love water. One time I knew somebody, this is a true story, they just like never drank water, ever. They'd be like, I don't know, I haven't had a drink of water in weeks. And I'd be like, what do you drink? And they would drink juice and Coke and sports drinks. It seriously concerned me. So please drink water. Water's crazy. You're going to find out water's kind of crazy. It can act as both an acid and a base. You didn't drink water for 4.5 years. What did you drink? And what made you decide to want to start drinking water? Did you have to go to the hospital? I mean, I know technically, oh gosh, Jonathan, I know technically like there's water content in other things. Kidney failure, oh, you've got to drink water. Like 70% of your body is like water. You need water. Okay, you're not going to die, Grayson. Don't listen to Jonathan, but still, please drink water. Okay, so let's draw a reaction here of water acting as an acid. All right, so NH3 is the base. Water is the acid. Acids donate their hydrogen, so it's going to give up a hydrogen. So ammonia is going to grab one of those hydrogens, and we are going to get, should probably draw a double arrow here, right? Because NH3 is a weak base. We're going to get NH4 plus. Uh-oh, I charged this thing earlier. And OH minus. Okay. All right, then water acting as a base. So that's water acting as an acid, giving up a hydrogen. When it's a base, it's going to accept a hydrogen from someone else. So here, HCl is the acid, and water is the base. And what we're going to get is H3O plus and Cl minus. All right, so again, we've written reactions like this before, so these should look familiar, but I just wanted to prove to you, remind you, water can act as both an acid and a base, just depending on who it's around, okay? So everybody knows somebody that acts differently depending on who they're around. But the weird thing with water, the story gets weirder, because water can do that with itself. So the best analogy I have for this is someone with like an alter ego. So I don't know. I don't know if you know anybody like that, but that's water, okay? Water can be an acid or base just with itself. So let's think about that. If we assign one of these molecules as the acid and one as the base, what's going to happen? What do you get? So the acid will give up a hydrogen ion, the base will accept one, and we will get acid. We'll get OH minus. So I need to write that first. OH minus and H3O plus. All right. Now, here's the deal. This happens to a small extent in all aqueous solutions. So acid-base solutions happen in water. So this is happening in like all acid-base reactions and solutions. What that means is all of these solutions carry some concentration of H3O plus and OH minus, all right? And because this is a reversible reaction, we can write a K expression for it. Just like we did earlier for weak acids, here's an expression just for particularly for, this is pure water. Nothing else is in here. So K would be equal to the concentration of the hydronium ion times the hydroxide ion divided by water. And just like we did for Ka, water is present to a way higher concentration, much larger number. So we're just going to remove water, remove H2O from the equation. So what's left is this right here. So this is the equation that I really want to hone in on. And we put a little W with K at this point. We call it the ion product constant. Ion because we have a cation and an anion. Product because we're multiplying their concentrations. Constant because K is always going to be the same at a particular temperature. So we call it Kw. So this is just for pure water, not for anything else, just for pure water. Kw is equal to what I have boxed in up there, H3O plus times the concentration of OH minus, okay? So there's Kw. All right, so we've covered a couple of equations today, Ka and Kw. And before we move on, how are they different again? Someone remind me. Oh, sorry, Kennedy. Ka. Tyler said Ka is for weak acids. Kw is for pure water, yes. And the actual equations themselves, Kw is written for a water molecule with another water molecule, pure water, and therefore you have H3O plus times the concentration of OH minus. The weak acid Ka equation is H3O plus times A minus, and you do have a denominator. You're dividing by the concentration of the weak acid, HA, right? I will write those things out, but we're still looking at this slide for a minute. You good, Kennedy? Okay. All right, so remind yourself of how those things are different. Just real quick, I'm going to write those out. There's K. Kw is different. H3O plus times OH minus. Okay. All right. We've already written these, so you don't have to rewrite them, but I just wanted to put them side by side for you. Okay. So one more thing about water, and then we're going to do some practice problems. As it's stated in the name, this is a constant value, okay? So at 25 degrees Celsius, and I'm not going to give you weird problems where I'm like at 27 degrees Celsius or I'm not. It's always going to be 25 degrees, so you can always bank on what I'm about to say. Okay. So Kw is going to be equal to, at 25 degrees Celsius, 1, it's really small, times 10 to the negative 14. You bet, Keegan. 1 times 10 to the negative 14. That's like the smallest number we've seen all day. All right. So if we plug this in to our equation, what we end up with is 1 times 10 to the minus 14 equals concentration of H3O plus times the concentration of OH minus. All right. Now, in pure water, these two things are equal to each other, okay? Because you can't disassociate between two water molecules and end up with a different number of H3O plus and a different number of OH minus. Every time you make one hydronium, you make one hydroxide. So the concentrations are going to be identical if you're in pure water. Okay, pure water, these are identical. So we could modify the formula, right? We could say 1 times 10 to the minus 14 equals x, if they're identical. In other words, we could say x squared, right? If we're looking for the concentration, we just say x squared. Is that okay to do? If they're identical, both call them x, so now it becomes x squared. So what are the concentrations? Let's solve for them. How do we solve for them at this point? Thank you, Glenn. The square root. So we'll take the square root of both sides. And what you find is that 1 times 10 to the minus 7 equals the concentration of H3O plus and the concentration, this is molar, by the way, of OH minus. All right, and this is just in pure water. I'm going to keep saying that. Why did we do x squared? Well, because we know the value for Kw is a constant at 25 degrees Celsius. Michaela, what? Is you trying to write because we're doing algebra? So Bradley, it's because the concentrations of hydronium and hydroxide are identical. Anytime water molecules dissociate, like what we wrote, right? Let me scroll back up. Right up here, where we wrote pure water, and you see two water molecules, we labeled one as the acid, one as the base. If one hydrogen gives away, or sorry, if one water molecule gives away a hydrogen and another one accepts one, we automatically make one hydroxide and one hydronium. One each. We can't make one product without the other. So the concentrations of these things in pure water are going to be identical. So we're just labeling them X. We say, okay, the concentration, we could call them both X. That's just something we threw in because we're trying to solve for their concentrations. And we know they're going to be the same. So instead of using two different variables like X and Y or A and B, I'm just calling both of them X. And so the equation becomes X times X is X squared. Does that make sense? Yeah, this is just, it is algebra. Makes sense. Okay. I hope that answers your question. Okay, practice problems with KW. We're gonna do 2 practice problems. We're getting close to the end of time here, but y'all don't let me forget to go back to that homework problem and solve for part B. After we do these, you're gonna know how to. So because we know the concentrations of KW, and we know the equation for KW, if we happen to know the concentration of one or the other, like H3O plus or OH minus in a solution with an acid or a base, we could always solve for the other one. That's what we're about to do. We're going to use KW to solve for either the concentration of OH minus or the concentration of H plus if their concentrations are different from these right here. Okay, because the moment we put some acid or base into pure water, that's going to mess with the concentrations of things. So, all right. Here's the question. What are the concentrations of hydrogen ions and hydroxide ions in a 0.1 molar HCl solution? So I have 0.1 molar HCl, and I want you guys to think first. Anytime I give you a question like this, the first thing you need to do, step 1, is identify what kind of acid you have. I mean, is it strong or is it weak? Or if it was a base, same step. Identify, is it a strong or a weak base? How do you know? Go look at the table from earlier. You guys remember that table? Do you have it? I would love to scroll all the way back up. That's like 20 slides. And I'll make all of you dizzy. Anybody know what kind of acid HCl is? It is strong. So HCl is a strong acid. So what does that mean? Let's write the dissociation reaction. HCl going to dissociate to H plus and Cl minus. Completely. So if initially I have 0.1 molar, the problem tells me that. I have 0.1 molar. I have none of these products, ions, starting out. But when it's all done, what will my final concentrations be? We actually kind of wrote this out way earlier at the beginning of lecture. We did an example with 1,000 molecules, remember? Okay, Cleanna said 0.1. So we'll get 0.1 molar of each of these things. We'll have none of our initial acid left over. It'll all be disassociated, all be used up. Okay, does that make sense what I just did? And I can only do this for a strong acid. I can't write that for a weak acid. So we actually already answered one of the questions. The concentration of hydrogen ions is going to be equal to 0.1 molar. And I knew that. I had to know what kind of acid it was, but I determined that from knowing I've got a strong acid. It's going to completely disassociate. So my final concentration of my product here will be equal to the initial concentration of my acid. But we still need to solve for the second question. What is the concentration of hydroxide ions? And this is where we're going to use KW, because guess what? KW equals concentration of H plus or H3O plus, they're interchangeable, times the concentration of OH minus. And we know that. We know Kw, and we now know that. H plus. So we're just going to plug those things in, rearrange, and solve for OH minus. Does that make sense? So Kw, I'm going to come right up here, is 1 times 10 to the minus 14. So I'm just going to plug everything in for Kw. So this is step number 2, by the way. Use Kw when we're solving for both hydroxide and hydrogen. And whoops, that's going to equal 0.1 molar times concentration of OH minus. So I just plugged in Kw and I plugged in my concentration of hydrogen ions. Now we divide both sides by 0.1 molar. Cancels on the right side. Step 2 is use Kw to solve for the ion that you're missing. So like if you have H plus, use Kw to solve for OH minus. Or if you have OH minus, use Kw to solve for H plus. So we should get 1 times 10 to the minus 13. Molar equals concentration of OH minus. So we see that the concentrations deviate wildly from pure water the moment you put a strong acid in there. All right. Questions on this problem? We're going to do one more just like it, but this time with a different substance, this time with NaOH. And I actually want to change up the number because I want you to see. So instead of saying we have 0.1, let's say we have 0.25. So now, same question. What are the concentrations of hydrogen ions and hydroxide ions if you have a 0.25 molar solution of NaOH? NaOH is a base. Is it strong or weak? It's strong. So it will completely disassociate. So if we start out, NaOH is going to break up into Na plus and OH minus. Initially, if we have 0.25 molar of our base, none of our products yet. When it's done disassociating, and it will happen, all of it will completely go. We'll have none of that left over, and we'll have 0.25 molar of the sodium ions and 0.25 molar of our OH minus ions. Okay, so we answered this part of the question. Concentration of OH minus is 0.25 molar. Okay. And step 2 is use Kw to solve for this time H plus. So plug in Kw, plug in your concentration of OH minus, solve for H plus. I'm gonna do that over here. Divide both sides by 0.25. I'm gonna need help with a calculator. I can't do this one in my head. Anybody get the answer already? Four times 10 to the negative 14. Okay. All right. So it's really small. Okay, so any questions on these two problems? How we use KW, identifying the strong acid and the strong base. Oops, sorry, I don't know what happened. Got one more problem, and we're kind of getting close to the end, and I want to go back and finish that homework problem from earlier. So, oh, this gets us to this idea that right here. A solution is considered acidic, basic, or neutral based on the concentrations of H plus and OH minus. All right. So it's acidic. We know in pure water, which is neutral, concentrations of H3O plus or H plus and OH minus are equal. Okay, so we can literally write that same thing down here. Concentration of H plus is going to be equal 1 times 10 to the minus 7. Concentration of OH minus will be the same thing in something that's neutral. If we have concentrations of these ions that are similar to these numbers, that's a neutral solution. But in an acidic solution, we're going to have way more H plus. Okay, so the concentration would be greater than 1 times 10 to the minus 7. And because these two, the multiplication of these two things equals a constant, if one goes up, the other has to go down. So the concentration of OH minus, we would have less of it. It would be less than 1 times 10 to the minus 7. We consider a solution with these kinds of characteristics acidic. And then lastly, for something that's basic, we have more OH minus and less H plus. So in a solution that's basic, the concentration of H plus we could say would be less than 1 times 10 to the minus 7. Concentration of OH minus would be greater than 1 times 10 to the minus 7. All right, so that's how we're going to begin to classify things, and then we're going to look at pH on Thursday. Because things that are acidic or things that are basic have a corresponding pH. And then lastly, I want to get to this problem with the milk down here, but last thing on the slide. If we know the concentration of one ion, we can always find the other using KW, because our equation right up here shows us the equation for KW. You always know KW, the value of it. You can always plug it in. If you know one concentration, you can find the other. We did 2 example problems of that. Okay, milk. I don't know what you think about milk. I really don't think of milk as acidic or basic, but it has an H plus concentration of 4.5 times 10 to the minus 7. So technically, what is it? Here, the H plus concentration is greater than 1 times 10 to the minus 7. 4.5 times 10 to the minus 7 is greater than 1 times 10 to the minus 7. So it is acidic, slightly, not very acidic, but a little bit. And then what is OH minus? Well, you would simply do KW. Okay, plug those things in. 1 times 10 to the minus 14 equals now 4.5 times 10 to the minus 7 times the concentration of OH minus. And you divide both sides by 4.5 times 10 to the minus 7. If anybody wants to calculate that for us. I would say when you start doing these things, and you're going to find a whole lot on Thursday, put this stuff in parentheses since you have exponents in your calculator. Okay, word of the wise, use parentheses. If you don't, and you don't put in parentheses, it'll only divide by 4.5. It won't divide by 4.5 times 10 to the minus 7. So what is our concentration of OH minus? Yeah, I'm going, Haley. I need this answer, and then we're doing part B. Anybody? Kendall, thank you. 2.22 times 10 to the minus 8. There we go. Boom. All right, screenshot it, take a picture. I'm about to scroll up. Close your eyes because I got to scroll up a lot. Okay, here we go. Let's go find that problem. Part B. All right, guess what? If we know the concentration of H plus, how do we find the concentration of OH minus? So again, you'll plug in your numbers for your problem, but we know H plus when we solved earlier was 0.02 molar. So you're just going to plug it into KW now. So OH minus, well, we know KW now 0.02 times the concentration of OH minus. So just divide both sides by 0.02. We know, sorry, I should have written 1 times 10 to the minus 14. Divide by 0.02. This is molar. Okay, so your concentration of OH minus will be whatever that equals. 1 times 10 to the minus 14 divided by 0.02. We'll learn how to do part C on Thursday, okay? All right, any questions? That's it for today. I will stick around. We're gonna have a study session 9:30 Thursday. Click my office hour link. I'm gonna work problems for chapter 9. And if we have time to do any chapter 10 stuff, I will. But your brains are probably gonna be fried after that and a lecture. So thank you for joining. Take care. Have a good week. Well, I almost just said have a good weekend. I'll see you again before the weekend. Will that be recorded for the people who aren't able to attend? Yes, Jordan. I'll record it Thursday and post it. All right, guys.